Today we're going to learn about Archimedes' Principle. So imagine I give you an object of a regular shape, and I say, what's its density? You might imagine that the easiest way to find the density would be to find a scale, put that object on the scale to find its mass, then measure the volume of that object somehow, and then you know that the density of an object is the mass divided by the volume. But what happens if you can't easily measure the volume of that object? Either it's irregular in shape, or you don't trust the methods you have. I'm going to show you today something that was invented supposedly by Archimedes many years ago as a way to determine the density of a material or an object without ever explicitly measuring its volume. So let's take our object and let's suspend it from a scale. Okay, that object experiences two different forces, a gravitational force and a tension, which is essentially the weight. So when this object is at rest, the tension force is equal to the gravitational force, which is equal to the mass of that object times gravity. Now imagine we take that object, which is still suspended from the scale, and we submerge it in a container that has a fluid in it of known density. Let's call it water for right now. That object has three forces on it: a gravitational force, a buoyant force, which we've discussed previously, and a tension from the scale, which is its new apparent weight, designated by this tick sign right up top. So when the acceleration is 0, we know that the gravitational force is equal to the buoyant force plus this new effective weight of the object. Since we know that the gravitational force is still mg, the buoyant force is the density of the fluid, water, times the volume of our object, times gravity, and our new effective weight. We can go ahead and solve for the volume of the object. It's equal to mg minus our new effective weight over the density of water times gravity. And then again, we know that the density of an object is the mass over the volume. So that means that the density of this object is just mass times gravity times rho H2O over mg minus our new effective weight. And you'll notice that we can simplify again to say that the weight when measured without our fluid times the density of the fluid over the weight minus the new effective weight gives us our expression for the density of the object. And this density of the object only depends on the weight when it was not in water the weight when it is in water, and the density of that water cup. All right, so if you'd like to put this into practice, I can give you a problem to do. Let's say we have an object which has a mass of 35 grams and a volume of 5 cubic centimeters. What is the apparent weight when it's submerged in water? All right. Well, we know that object, like on the last slide, has a gravitational force associated with it. It has a buoyant force, and it has an effective weight. We set these forces equal to each other. And we get that the effective weight, oh, sorry about that. The effective weight is equal to the gravitational force minus the buoyant force, which is equal to mg minus the density of water, the volume of the object, gravity. Distribute some terms, mass minus density, the volume, (10 meters per second squared times 0.35 kilograms minus 10 to the 3 kilograms per meter cubed, which is the density of water, and the volume of that object is 5 centimeters cubed, and then another factor to change that into the right units. So we have 10 to the 2 centimeters per meter, and we need to cube that. And if you plug in all of those things, you get 0.3 newtons. There you go. So that would be the effective weight of this object if it was measured while it's submerged in a fluid. Now, something that we should probably check is we're assuming with our buoyant force that the entire object is submerged. Right? If the entire object is not submerged, the buoyant force only depends on the volume of fluid that's displaced. So for this solution to be correct, we know that the whole object has to be totally submerged in water, which means that the density of the object has to be greater than the density of the fluid. So what is the density of this object? That is the mass of the object, which is 0.35 kilograms, and the volume of the object is 5 centimeters cubed, 10 to the 2 centimeters per meter cubed. Let me get my calculator. That equals 7 times 10 to the 3 kilograms per meter cubed, which is greater than the density of water, which is equal to 1 times 10 to the 3 kilograms per meter cubed. So there you have it. Now you have a way to calculate the density of an object without ever measuring its volume, or a new way to measure what the mass or the weight of an object would be while it's submerged. Hope you enjoyed.